The question is not about the origin of the voltage, since there wasn't any, but what could have caused the voltage sniffer to malfunction. My speculation is that the voltage sniffer is detecting stray voltage from nearby electrical wiring or equipment. Stray voltage is a common occurrence in electrical systems, and a range of factors can cause it, including loose connections, compromised insulation, or electromagnetic interference. The wires hanging from the beam might not be properly grounded, allowing stray voltage to flow through them and into the voltage sniffer. Another possibility to consider is the tool itself may be experiencing problems. While less probable, it is still a potential explanation. If doubts arise regarding the accuracy of your voltage sniffer, having it calibrated by a qualified electrician is recommended. A thorough examination of the electrical system for any loose connections or damaged insulation is also advisable. Several things can cause this to happen. Firstly, capacitive coupling can occur. Even if the wires aren't connected to a live circuit, they can pick up a signal from nearby energized conductors through capacitive coupling. The voltage sniffer, being highly sensitive, might interpret this induced signal as live voltage. Secondly, electrostatic charge can build up on a grounded conductor. This charge, especially in dry environments, can trigger a voltage sniffer. Thirdly, electromagnetic interference, or EMI, from nearby electronic devices or radio transmitters can interfere with the sniffer's readings. Voltage sniffers are designed to detect electromagnetic fields associated with alternating current voltage. Strong EMI can create false positives. Fourthly, some voltage sniffers are more sensitive than others. A cheaper or poorly designed sniffer might be prone to false readings. Fifthly, the environment plays a role. Humidity, temperature, and the presence of other materials can affect the sniffer's performance. For instance, the damp environment can increase conductivity and lead to false readings. Sixthly, the wires themselves might be acting as antennas, picking up ambient electromagnetic radiation. Seventhly, the beam's material, if metallic, could be influencing the electromagnetic field around the wires. Eighthly, if the wires are close to a grounded object, it could create a capacitive divider effect, making the sniffer detect a voltage even if there's no actual source. Ninthly, static electricity from clothing or the person holding the sniffer can sometimes cause false readings, especially in dry conditions. Tenthly, some types of non-contact voltage testers can give false positives if they are not properly grounded. Try touching a grounded metal object while using the tester to see if it makes a difference. To troubleshoot the situation, firstly try a different voltage tester. If the second tester doesn't detect voltage, it's likely the first one is faulty or overly sensitive. Secondly, turn off the power to the nearby circuits, if possible, and see if the voltage indication disappears. If it does, it confirms that stray voltage is the issue. Thirdly, check the grounding of nearby electrical equipment and wiring. Poor grounding can exacerbate stray voltage problems. Fourthly, move the wires away from any potential sources of interference, such as electronic devices or other wiring. Fifthly, test the sniffer in an under-energized area to ensure it's not simply malfunctioning. Sixthly, try grounding the wires temporarily to see if it eliminates the false readings. Seventhly, consult the voltage sniffer's manual for troubleshooting tips and limitations. Eighthly, consider the environment. Is it particularly dry or humid? Could there be sources of EMI nearby? Ninthly, if the problem persists, call a qualified electrician to investigate further. They can use more sophisticated equipment to identify the source of the stray voltage and correct any underlying issues. Tenthly, remember that voltage sniffers are intended as a preliminary safety check, not a definitive diagnostic tool. Always verify the absence of voltage with a properly calibrated multimeter before working on any electrical circuit. Regarding the possibility of a malfunctioning sniffer, it is essential to consider the device's condition and history. Firstly, check the battery. A low battery can cause erratic behavior in electronic devices, including voltage sniffers. Secondly, inspect the sniffer for any signs of physical damage, such as cracks, dents, or loose components. Damage can compromise its accuracy and reliability. Thirdly, consider the sniffer's age. Over time, electronic components can degrade, leading to inaccurate readings. Fourthly, check the sniffer's calibration date, if applicable. Some voltage sniffers require periodic calibration to maintain accuracy. Fifthly, compare the sniffer's performance to a known working unit. If the suspect sniffer consistently gives different readings than a reliable one, it is likely malfunctioning. Sixthly, review the sniffer's manual for troubleshooting tips and error codes. The manual may provide guidance on diagnosing and resolving common issues. Seventhly, if the sniffer has been exposed to extreme temperatures, humidity, or other harsh conditions, it may be damaged. Eighthly, if the sniffer has been dropped or subjected to excessive vibration, its internal components may have been dislodged or damaged. Ninthly, if the sniffer has been used in a dusty or dirty environment, its sensor may be contaminated, leading to inaccurate readings. Tenthly, before assuming the sniffer is malfunctioning, double-check that it is being used correctly, following the manufacturer's instructions. Stray voltage can be a complex issue, and pinpointing the exact cause often requires a systematic approach. Firstly, identify potential sources of stray voltage in the vicinity. This could include nearby electrical equipment, wiring, transformers, or even grounding systems. Secondly, use a multimeter to measure the voltage between the wires and a known ground point. This can help determine if there is indeed a voltage present and its magnitude. Thirdly, check the grounding system for any faults, such as loose connections, corroded components, or improper grounding techniques. A faulty grounding system can contribute to stray voltage problems. Fourthly, inspect the wiring for any signs of damage, such as cracked insulation, exposed conductors, or loose connections. Damaged wiring can leak voltage and create stray voltage paths. Fifthly, consider the possibility of electromagnetic interference from nearby electronic devices or radio transmitters. EMI can induce voltage in nearby conductors, leading to false readings. Sixthly, analyze the wiring configuration to identify any potential capacitive coupling effects. Capacitive coupling can occur when conductors are run parallel to each other over long distances, inducing voltage in the unenergized conductor. Seventhly, check for any unbalanced loads in the electrical system. Unbalanced loads can create neutral currents that contribute to stray voltage. Eighthly, consider the presence of harmonics in the electrical system. Harmonics can create voltage distortions that can be detected by voltage sniffers. Ninthly, if the problem persists, consult with a qualified electrician or electrical engineer to conduct a thorough investigation of the electrical system. Tenthly, remember that stray voltage is not always a safety hazard, but it can be a nuisance and can interfere with the proper operation of electronic equipment. Mitigation techniques, such as proper grounding, shielding, and filtering, can be used to reduce stray voltage levels. Calibration of a voltage sniffer is an important process to ensure its accuracy and reliability. Firstly, understand the calibration process. Calibration involves comparing the sniffer's readings to a known voltage source and adjusting it to match the standard. Secondly, gather the necessary equipment. You will need a calibrated voltage source, a multimeter, and the sniffer itself. Thirdly, refer to the sniffer's manual for specific calibration instructions. Different models may have different procedures. Fourthly, connect the sniffer to the calibrated voltage source. Follow the manufacturer's instructions for proper connection. Fifthly, compare the sniffer's reading to the voltage source's reading. If there is a discrepancy, adjust the sniffer's calibration settings. Sixthly, use the multimeter to verify the sniffer's reading. The multimeter provides an independent measurement for comparison. Seventhly, repeat the calibration process at different voltage levels to ensure accuracy across the sniffer's range. Eighthly, document the calibration results. Keep a record of the calibration date, the equipment used, and the adjustments made. Ninthly, schedule regular calibration checks. Over time, sniffers can drift out of calibration, so periodic checks are necessary. Tenthly, if you are not comfortable performing the calibration yourself, consider sending the sniffer to a qualified calibration lab. Loose connections are a common cause of electrical problems and can contribute to stray voltage. Firstly, identify potential loose connections. Look for signs of corrosion, discoloration, or physical damage at connection points. Secondly, use a screwdriver or wrench to tighten screws and nuts on electrical connections. Ensure they are snug but not over-tightened. Thirdly, check wire connectors for proper crimping. Loose or poorly crimped connectors can cause resistance and heat. Fourthly, inspect wire splices for secure connections. Loose splices can create intermittent electrical problems. Fifthly, examine terminal blocks for loose wires. Terminal blocks are often used to connect multiple wires together. Sixthly, check circuit breaker connections for tightness. Loose connections on circuit breakers can cause tripping or overheating. Seventhly, inspect the connections at electrical outlets and switches. Loose connections can cause flickering lights or non-functioning devices. Eighthly, use a voltage tester to verify that connections are properly energized after tightening. Ninthly, if you find any loose connections, turn off the power to the circuit before working on it. Tenthly, consider using a torque wrench to tighten connections to the manufacturer's recommended torque specifications. This ensures a consistent and reliable connection. Damaged insulation can compromise the safety and performance of electrical wiring. Firstly, identify potential areas of damaged insulation. Look for cracks, cuts, abrasions, or discoloration on the insulation. Secondly, use a multimeter to check for continuity between the wire and ground. Continuity indicates a breach in the insulation. Thirdly, inspect the wiring in areas where it is exposed to heat, moisture, or chemicals. These factors can accelerate insulation degradation. Fourthly, examine the wiring in areas where it is subject to physical stress, such as bending or flexing. Stress can cause insulation to crack or break. Fifthly, check the wiring in areas where rodents or insects may have access. These pests can damage insulation by chewing or nesting. Sixthly, if you find any damaged insulation, turn off the power to the circuit before working on it. Seventhly, repair damaged insulation with electrical tape or heat shrink tubing. Ensure the repair is properly sealed and covers all exposed conductors. Eighthly, replace severely damaged wiring with new wiring. Use the same gauge and type of wire as the original. Ninthly, protect wiring from future damage by using conduit or other protective coverings. Tenthly, consider hiring a qualified electrician to inspect and repair any damaged insulation. Improper grounding can create a variety of electrical hazards and can contribute to stray voltage. Firstly, understand the purpose of grounding. Grounding provides a low impedance path for fault currents to flow back to the source, tripping the circuit breaker and preventing electrical shock. Secondly, check the grounding electrode system. This typically consists of a ground rod or ground plate buried in the earth. Thirdly, verify that the grounding electrode conductor is properly connected to the grounding electrode. The grounding electrode conductor connects the grounding electrode to the electrical panel. Fourthly, inspect the main bonding jumper. The main bonding jumper connects the neutral conductor to the grounding conductor in the electrical panel. Fifthly, check equipment grounding conductors. Equipment grounding conductors connect the metal enclosures of electrical equipment to the grounding system. Sixthly, verify that all electrical outlets and switches are properly grounded. Use a receptacle tester to check for proper grounding. Seventhly, inspect the grounding system for any signs of corrosion or damage. Corrosion can reduce the effectiveness of the grounding system. Eighthly, test the ground resistance of the grounding electrode system. High ground resistance indicates a problem with the grounding system. Ninthly, if you find any problems with the grounding system, consult with a qualified electrician to correct them. Tenthly, ensure that the grounding system meets the requirements of the National Electrical Code, NEC Section 250. An unbalanced load in an electrical system occurs when the current draw on each phase of a multi-phase system is not equal. Firstly, understand the concept of balanced loads. In a balanced system, the current draw on each phase is equal, resulting in minimal neutral current. Secondly, identify potential sources of unbalanced loads. Single-phase loads such as lighting, appliances, and electronic equipment can contribute to unbalanced loads. Thirdly, use a clamp meter to measure the current on each phase of the electrical system. This will reveal any imbalances in the current draw. Fourthly, analyze the distribution of loads on each phase. Try to distribute loads evenly across all phases to minimize imbalances. Fifthly, consider the use of three-phase equipment. Three-phase equipment draws current evenly from all three phases, helping to balance the load. Sixthly, check for any oversized or undersized conductors. Oversized conductors can carry more current than necessary, while undersized conductors can overheat and cause voltage drop. Seventhly, inspect the neutral conductor for excessive current. High neutral current indicates an unbalanced load. Eighthly, use a power quality analyzer to monitor the electrical system for harmonics and other power quality problems. Harmonics can exacerbate unbalanced load problems. Ninthly, if you find any significant imbalances in the load, consult with a qualified electrician to correct them. Tenthly, regularly monitor the electrical system for unbalanced loads to ensure efficient and reliable operation. Harmonics are distortions in the sinusoidal waveform of alternating current voltage or current. Firstly, understand the concept of harmonics. Harmonics are multiples of the fundamental frequency of the electrical system, typically 60 Hz. Secondly, identify potential sources of harmonics. Nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces, can generate harmonics. Thirdly, use a power quality analyzer to measure the harmonic content of the electrical system. This will reveal the presence and magnitude of harmonics. Fourthly, analyze the harmonic spectrum to identify the dominant harmonic frequencies. Different types of equipment generate different harmonic frequencies. Fifthly, consider the use of harmonic filters. Harmonic filters are designed to reduce the levels of specific harmonic frequencies in the electrical system. Sixthly, check for any overheating of transformers, conductors, or other electrical equipment. Harmonics can cause increased heating due to increased current flow. Seventhly, inspect the neutral conductor for excessive current. Harmonics can cause increased neutral current, leading to overheating and damage. Eighthly, use shielded cables and grounding techniques to reduce the effects of harmonics. Shielded cables can prevent harmonics from radiating into other equipment. Ninthly, if you find any significant levels of harmonics, consult with a qualified electrician or electrical engineer to correct them. Tenthly, regularly monitor the electrical system for harmonics to ensure efficient and reliable operation. Regarding the NEC, firstly, Article 100 defines terms such as ground, grounded, and grounding electrode conductor. Secondly, Article 250 covers grounding and bonding requirements for electrical systems. Thirdly, Section 250.4 addresses general requirements for grounding and bonding. Fourthly, Section 250.24 covers grounding of service equipment. Fifthly, Section 250.50 covers grounding electrode systems. Sixthly, Section 250.66 covers sizing of grounding electrode conductors. Seventhly, Section 250.118 lists acceptable grounding conductors. Eighthly, Section 300.3 addresses conductors of different systems in the same raceway or cable. Ninthly, Article 310 covers conductors for general wiring. Tenthly, Article 408 covers switchboards and panel boards. The NEC provides comprehensive requirements for grounding and bonding to ensure electrical safety. Consulting with a qualified electrician can help ensure compliance with the NEC. Mitigation techniques for stray voltage include proper grounding, shielding, and filtering. Firstly, proper grounding. Ensure that all electrical equipment and wiring are properly grounded according to the NEC. This provides a low impedance path for fault currents to flow back to the source, reducing the risk of electric shock. Secondly, shielding. Use shielded cables and enclosures to prevent stray voltage from radiating into surrounding areas. Shielding can block electromagnetic interference that can induce voltage in nearby conductors. Thirdly, filtering. Install filters on electrical equipment to reduce the levels of harmonics and other electrical noise that can contribute to stray voltage. Filters can remove unwanted frequencies from the electrical system, improving power quality. Fourthly, isolation transformers. Use isolation transformers to isolate sensitive equipment from the main electrical system. Isolation transformers provide a barrier to the flow of stray voltage, protecting sensitive equipment from damage. Fifthly, surge protection. Install surge suppressors to protect electrical equipment from voltage spikes and surges. Surge suppressors can clamp voltage surges to safe levels, preventing damage to equipment. Sixthly, line conditioning. Use line conditioners to regulate voltage fluctuations and provide a stable voltage supply to sensitive equipment. Line conditioners can improve power quality and reduce the risk of equipment malfunction. Seventhly, grounding electrodes. Install additional grounding electrodes to improve the effectiveness of the grounding system. Additional grounding electrodes can lower the ground resistance and provide a more reliable path for fault currents. Eighthly, equipotential bonding. Bond all metal objects in an area together to create an equipotential plane. This minimizes the voltage difference between objects, reducing the risk of electric shock. Ninthly, regular inspections. Conduct regular inspections of the electrical system to identify and correct any potential problems. Regular inspections can help prevent stray voltage and other electrical hazards. Tenthly, qualified personnel. Hire qualified electricians to perform all electrical work. Qualified electricians have the knowledge and experience to ensure that electrical systems are installed and maintained safely and correctly.